A given function, determine if the function is continuous at those three x values. So if you would write that function down, we'll talk about what type of function this is. We can graph this, but by the time we graphed it, we could have answered three of these types of questions. So we're going to first try this algebraically. If you don't like the algebraic, then we will go ahead and graph it. This is what's called a piecewise defined function, because it's made up of several pieces of other functions. In fact, we have 4 different functions going on here. Okay. To determine continuity, we have to check 3 things. Again, does the function exist? Does the limit exist? And are they the same numbers? All right. Remember, to test if the limit exists, when we're approaching numbers, we plug that number in. Okay. So let's start with x equals -3. That's part A. I'm going to use the highlighter. It's so cool. I don't know, should I use the highlighter? I'm not going to use the highlighter. I'm going to use the highlighter. I don't know how to erase the highlighter, so we might be stuck with this guy. Notice we have, there was no point in that, really. I mean, I'm just going to smiley face. It's cute. Technology, love it. Anyways, notice the -3 is, referred to by 2 different functions, x squared and y equals 9. If we were to plug in -3, because this would be on the left, I apologize. This one's on the left because this is all the values to the left of -3. Left and at equal to -3. So the left-hand limit would occur when we plugged in -3 into this function. What would we get? 9. The right-hand side, notice this is to the right of -3. If we plug -3 into this function, notice it's a constant function, which means it doesn't change. What would we get? 9. So the left-hand limit's 9, the right-hand limit's 9. So what's the limit itself? 9. Okay. So we have the limit as x approaches -3 of our function is 9. So that part checks out. 2. Let's find f of -3. Well, notice this inequality has the equal to. So this is the section of the graph where x can equal -3. So if we plug in -3 into the function, what do we get? 9. So the limit equals 9, the function equals 9. So is it continuous at -3? 9 equals 9. Continuous. Let's try 4. B, x equals 4. So let's start with the limit. So notice these 2 parts of the graph deal with x equals 4. Okay? So if we plug in 4 into this part, the left-hand side, what would we get? 9. If we plug in 4 to the right-hand side, what would we get? So what does the limit equal? All these 9s. It's like that Beatles song. No? It's called 9? White Album? Anyone heard of the Beatles? No? Okay. I think they're from Australia. Alright, let's try f of 4. Well, notice, neither of these inequalities have an equal to. So what's f of 4? Undefined, does not exist. In other words, there's a hole in the graph there. So do we even continue with the third case? No. What's our conclusion? What happens at x equals 4? Well, as far as if it's continuous or not. Yeah, so we call it discontinuous. If you would, please try part C on your own, x equals 6. So what's the limit as x approaches 6 of f of x? Does not exist. Why? Correct. So the left-hand limit's 11, the right-hand limit's 2. 11 doesn't equal 2. So since the left-hand limit doesn't equal the right-hand limit, the limit doesn't exist. And we stop. Because if the limit doesn't exist, then it can't be continuous. So very good. This is also discontinuous. There's an extra hump right there. Oops. Part D! Mike, there's no part D! Well, there is now. X equals 5. Try this one on your own. So x equals 5 is in this section because 5 is between 4 and 6. But what type of function is this? It's a polynomial. Specifically, it's a linear function. And what do we know about polynomials? They are continuous all the time. Well, notice there's no breakup at 5. This whole range from 4 to 6 is okay. So since 5 is in between them, then it's automatically continuous, because this happens to be a polynomial. So the left-hand limit is the right-hand limit, namely 10. The functional value is 10. We're good to go. So that's where those shortcuts come into play.